Our most eminent speaker, I want to invite our director on stage now so that he can do the proper introductions. Thank you very much.
Good evening. It's a great pleasure for me to welcome all of you on this special occasion. Thanks to Cefipra and the French Consulate for having with us one of the most distinguished physicists that probably the world has seen. And it's our singular honor that IIT Bombay is hosting Professor Serge Haroche in our campus. We had a great day in terms of having discussion sessions, various meetings, and I'm sure that that has ignited the minds of many of our students in terms of what all can be done, new frontier areas, and in this particular area, probably the person whom we all look forward to the kind of developments that he has done and for which he recognized is Professor Serge Haroche. Very briefly, I think he doesn't need any introduction, particularly if you are a physicist. So I will not take much time because rather it would be mostly we want to hear from him. So let me introduce that Professor Serge Haroche was awarded the Nobel Prize in Physics in 2012 for developing his groundbreaking methods that enable measurement and manipulation of individual quantum systems. He has pioneered a research field called cavity quantum electrodynamics, which plays an important role in the development of quantum information science. He is an emeritus professor at the Collège de France in Paris and a member of the French Academy of Sciences. But what is very interesting is that this is not his first visit to our campus. This is his second visit after receiving the distinguished Nobel Prize. He was here in the campus in 2015 under TechFest, where the campus had the opportunity to listen to him. But that being 2015, many of our students might have graduated. Of course, some of the professors are still there, and the memory remains, but there are new students, and I think it'll be a wonderful occasion for all of us to get this opportunity to listen to him. Thank you, and let's welcome him.
Thank you very much for your kind welcome. I remember I was here in 2015, and I was very much impressed by the number of students, their enthusiasm, their willing to learn about physics, their eagerness to ask questions about fundamental things. It was 8 years ago, and my field of research has evolved a lot during that time interval, and so I will be talking about new things, new experiments which were not possible in 2015. I have decided to talk about quantum information with Rydberg Atoms. Rydberg Atoms are the systems which I have used during my career to make the experiments in cavity quantum electrodynamics, which were, I think it's okay like that? Can you hear me? Okay.
Yeah, it's muted now. You can unmute.
So Rydberg atoms are very round, and it means that this atom is sensitive to very small perturbations. And when I started working on these atoms, I was interested in their interesting experiment in the field of quantum become a very active field of research in quantum information science. So I will talk about these two areas, briefly about interaction of Ringback atom with microwave cavities, and more extensively about the experiments which are being done now, trying to take advantage of the interaction between Rydberg atoms. First of all, just to set up the context of this talk, I will remind you that we are now in the process of witnessing what is called the second quantum revolution, which is taking advantage of the fact that we can manipulate single quantum systems in order to achieve tasks which were impossible before that, and to take directly advantage of the quantum superposition and quantum entanglement to develop practical devices. One field is, of course, quantum metrology. It's a field in which we want to take advantage of the fact that these quantum systems are very fragile, very sensitive to perturbation, and one can thus use them in order to measure things with a precision, with a sensitivity which is much higher than what we could do previously. I give you here two examples. These figures show what is called the Wigner function of a cavity field or of an atom. What's the problem? You want to dim the light? Okay. You see that if you can prepare a quantum system in the state which is described with by this kind of Wigner function, the system becomes very sensitive to small changes. For example, on the picture that you see on the left of this slide, you see a squeezed state of light, a state of light which has very much smaller fluctuation for one phase of the field than for the other, and you can use this kind of field states to measure, for example, small variation of distances between mirrors with a very high precision, and this is a kind of light which is now used in gravitational wave detectors, big antennas which detect the gravitational waves coming from outer space. On the right part, you see the Wigner function of what we call a Schrödinger cat. It's a system which has two different positions corresponding to the two spots that you can see on the top and at the lower level. And in between, you see very narrow interference fringes. These fringes can move very easily if you perturb the system, and then can be used, for example, to measure electric or magnetic fields with a precision much higher than with an ordinary classical detector. So this is quantum metrology, and there are a lot of achievement in this field, in particular for optical atomic clocks. The second domain that I want to discuss is quantum communication, which is a field in which one sends, for example, two entangled photons in two different regions of space, and the partner which gets these photons can use the detection of this photon in order to exchange cryptographic keys in a way which cannot be spied upon, and this is the basis of quantum communications, which is another field which exploits quantum logic. And one way to do it is to go through a satellite and to make a communication in free space using a satellite as a relay, and it's a very active domain of research in various countries. Quantum simulation is also an interesting field in which you can position atoms, real or artificial atoms at well-defined position, let them interact with each other, and try to use the system to simulate situations which occur in condensed matter physics. I won't say more about that because this will be the main topic of the talk. And of course, the last field is quantum computing, which is a very far away goal, a kind of utopian today, which will use state superposition and entanglement of qubits to solve problems that classical machine cannot do. And it's a very challenging domain because decoherence destroys very quickly the quantum superposition, which would make quantum computing effective. So there is a lot of research to be done to try to overcome the decoherence to get this machine working. One example of system in which quantum computers are being built is a quantum superconducting devices, and you see here a picture of a cryostat with quantum circuits at the top, at the bottom of this system. What are the qubits candidates, the elementary units that are candidates to build this kind of machines? One is, of course, cold atoms, which are trapped in an optical lattice, and there is a lot of experiments in this domain all around the world. Another system is trapped ions, trapped between in a set of electrodes. The ions are maintained by electromagnetic forces, either on a line or in a plane or even in a 3D structure. Another domain is photon, entangled photons, which can be produced by down conversion in nonlinear crystals. You have also the field of nitrogen vacancy centers in diamond, which can produce single photons and be used to build sensors. We had a talk about that before mine. You have also quantum dots, superconducting qubits, which I already mentioned, and you have also layered structures of Bragg diffraction, which can trap photons inside a system which looks like cavity QED. Vertical lasers, post-microscopic lasers are made with a system in which you can have polaritons, mixed states of matter and light, producing quantum effects. And the last domain, of course, are photons and Rydberg atoms in cavities, or Rydberg atoms interacting between each other, and this is a domain that I would like to cover in this talk. So I will start by a brief history of Rydberg atom physics. The name comes from the Swedish physicist Rydberg, who was the first one to find in the spectrum of atoms, even before quantum physics, that there were states of the atomic system which were interesting. Now we prepare these Redberg atoms by exciting an ordinary atom, usually an alkali like rubidium, cesium, or sodium, using laser excitation to promote the outer electron to a very large orbit. So you see you have the core of the atom, which contains the nucleus and all the electrons save one, and one electron is roaming very far from the core on a large orbit. The energy levels of this atom are very easy to compute. It's a kind of hydrogen system. So the energy scale is as 1 over n squared, where n is a principal quantum number, which takes integer values. And you have a very small correction, which I have written here as delta, which takes into account the core perturbation, the fact that it's not exactly hydrogen, that there is slight perturbation coming from the fact that this electron going around produces kind of tides in the ion core structure, which slightly shifts the energy levels. So it's a system which looks very much like hydrogen, which has a very big size and a long lifetime. And it is very sensitive to external fields, because as soon as, for example, the external electric field is of the order of the field seen by the outer electron, which is a small field because it's very far from the nucleus, the perturbation becomes large. And so this is a very sensitive probe of environment, in particular of microwave radiation. And it's also very sensitive to the interaction of Rydberg atoms with each other. Of course, these atoms have been in physics for a long time. I mentioned already Rydberg. We established the formula which gives the frequency of spectral lines, which converts toward the ionization limit of the atom. If you increase the principal quantum number, you reach the point where the electron will be ejected from the atom when n goes to infinity. In 1913, Bohr used the Rydberg formula to understand the structure of the atom, and he introduced the first quantum laws, which explain why you have this 1 over n squared dependence of the energy levels of the atom. In the 1930s, another famous physicist, Enrico Fermi, did some kind of atomic physics, and he studied the shifts produced on the spectral lines of alkali atoms when the atoms are immersed in a buffer gas, in a gas of neutral of noble gases like helium or xenon or krypton. And the Rydberg atom is so big that there is a lot of small noble gas atoms inside the orbit. And these atoms behave as a kind of dielectric medium which perturbs the energy levels. Fermi studied that, and he introduced the notion of scattering length of the wave function of the outer electron. And this notion of scattering length since then extended to describe phenomena in nuclear physics and in cold atom collisions. So it's a very important concept which was born from Rydberg atom physics. Finally, I should mention the fact that Rydberg atoms with large n values are produced by capture of electrons on ions in interstellar space, and they cascade down in the energy level by emitting microwave photons, which are detected by radio telescopes. And so in astrophysics, these Rydberg atoms have been known for quite a time. In the 1970s, when the lasers have become available, one has started to study the Rydberg atom in laser spectroscopy. So the way to excite them is a stepwise excitation. You start from the ground state, here it's the case of sodium, you go to the first excited state, and before the atom decays with a second laser, you bring the electron to a very large orbit, very small binding energy, very close to the ionization limit. And so we started with my research group and other groups in the world to study these spectra close to the ionization limit. When you excite the atom with lasers, you excite them in low angular momentum states which have classically very elliptical orbits, which can get very close, in which the electron can get very close to the nucleus when it is at the closest range from the nucleus. These low L states are accessible with lasers, but if you want to go to higher end state with angular momentum equal to 2, 3, 4, and so on, you cannot access directly from the ground state because of energy of momentum conservation. Each photon carries only 1 unit of angular momentum. You need to have the atom absorb a lot of radio frequency photons with almost the same energy. And you do that by microwave spectroscopy between the Rydberg levels. And in the end, you can reach the state which has the highest possible angular momentum, in which the electron is going on a circle around the nucleus. This is called a circular Rydberg atom. It is the atom which was studied theoretically by Niels Bohr in the famous 1913 paper, and it is the simplest of all possible atoms, just an electron going on a circle around the nucleus. You can compute the energy of this atom, its lifetime, all its properties by classical physics, just back of the envelope calculation using Coulomb's law and simple radiation law coming from Maxwell's equations. This circular atom has an orbit with radius scales as n squared, so it increases very fast with the principal quantum number. And you can give it a very simple explanation in terms of de Broglie wavelengths. In fact, it's a kind of running wave going around on a circle, and the quantization condition is that you have an integer number of de Broglie wavelengths on the circumference. When you express that, you find Bohr's law. So it's a very simple, and I think it's the way de Broglie understood that the electron was a wave, that he could retrieve Bohr's law by this simple argument. In order to prepare this circular state by laser excitation, you have first to absorb a few optical photons and then to absorb circularly polarized radio frequency photons, and in order to feed angular momentum into the system. And for this microwave to be resonant, you need to remove the degeneracy in the manifold of a given n in order to have a ladder of states through which the radio frequency can be absorbed. I just show it very briefly on this slide. You see the process here is use 3 optical photons, so you get into the 52F state. You apply an electric field which removes the degeneracy in this state, giving the structure of this triangular structure that you can see on the picture. And then you use radio frequency photons to adiabatically excite the atom, feed angular momentum until you get in the state which has a maximum angular momentum. And then you can also make a microwave transition which brings you to the final state, in this case, n equal 51, which is a kind of circular state that we are using in our experiments. Now, why are these states interesting is shown on this table where I mentioned what are the exaggerated features of these Redberg atoms. The first, I compare the properties of a ground state or low excited atom with a Redberg atom. First property is the orbital size, which is related to the electric dipoles that you can build in the system when you separate the electron from the nucleus. In an ordinary atom, this distance is of the order of 1 angstrom, 10 minus 10 meter. Its scale is an n square, which means that if you go to n equal 100, the atoms now is 4 orders of magnitude larger and gets a size of 1 micrometer, which is the size of a bacteria or a virus. So you get really something which is macroscopic at the atomic scale. Second property is the radiative lifetime. This lifetime scales as n cubed or n to the fifth, depending upon whether the angular momentum is small or large. For weakly excited state, this lifetime is of the order of a few nanoseconds, typically 10 minus 8 seconds. The time it takes for the excited electron to fall back on the ground state. If you are in a Rydberg state, this lifetime becomes of the order of 10 minus 5 seconds, 10 minus a few microseconds for low angular momentum state, and can reach 1 second for the circular state for n equal 100. Why so long? Because the acceleration on a circular orbit is the weakest possible acceleration. And you know classically that the radiation is proportional to the square of the acceleration of the electron. So these high angular momentum states have a very weak radiative decay. So they are almost stable. Third property, the spacing between states. It scales as n minus 3. For low excited state, it falls in the optical range, 10 to the 14 to 10 to the 15 hertz. So it's why atoms absorb or emit visible radiation. But if you go and look at the transition between Rydberg atoms, it falls in the range of the gigahertz or a few gigahertz, which explains that these atoms are very sensitive to microwaves. They resonantly absorb or emit microwaves. The last property which will be of interest here is the atom-atom coupling, the so-called van der Waals interaction. Each atom has an electric dipole. The fluctuation of the dipole on the first atom induces a dipole on the second. These two dipoles, which are correlated by this fluctuation, are coupled, and the coupling scales as n to the 11 over r to the 6. So it decreases very fast with distance, but it's enormously enhanced when you go to a Rydberg state. For low excited state at 1 nanometer, that is at about 10 angstrom from each other, the van der Waals interaction is about 100 megahertz. If you go to Rydberg states, the same 100 megahertz energy shift is produced at 10 micrometer instead of 10 nanometers. So you win a factor of 1,000 on the distance over which the interaction can be observed. And so this is an effect which is huge and which will lead to interesting application in the context of the experiment I will be describing. We have used two cavity QED setups in our experiments. The first one is just a horizontal beam. We excite the atoms into a Rydberg state, and they cross horizontally at a thermal velocity, a cavity which is made of two high-quality mirrors facing each other, superconducting mirrors. The atoms have a velocity between 200 and 300 meters per second, and they cross the cavity in about 100 microseconds. So we have to do the experiment rather fast before the atom fly out of the cavity. Then we went to a system in which the beam is vertical, and we use slow atoms. The atoms are prepared at the bottom in a cold atom system. It's called a magneto-optical trap. And using a laser beam pointing upwards, we push the atoms across the apparatus in a kind of atomic fountain. They are much slower. They have a velocity of a few meters per second, and it takes a time up to 1 millisecond to cross the cavity, so we have much more time to do interesting experiments. And I show you here the experiment. The first experiments we did is what is called vacuum Rabi oscillation. What we do is that we send in the cavity an atom which is in the upper Rydberg state, and the cavity is resonant with a transition to the state which is immediately lower, with n equal to n minus 1. And so the atom can emit a photon and go to the lower state. And then, since the photon stays in the cavity, the photon can be reabsorbed, and the atom comes back to the upper state. And the atom goes back and forth while the photon number goes from 0 to 1. So in 1996, we could observe only 4 Rabi oscillations because the cavity was crossed quickly. With a vertical atomic beam, we can observe up to 20 oscillations, and we can see this quantum phenomena much better. What we observe, in fact, in this experiment is a periodic exchange between the two circular states n and n minus 1, correlated with the presence of 0 or 1 photon in the cavity. what we see, in fact, is a superposition of the state in which the atom is excited with 0 photon and the atom is in the lower state with 1 photon. And the amplitude of this superposition oscillates at what is called the vacuum-Rabi frequency, which expresses the fundamental coupling between the atom and the field. This expression that you see on this transparency is typically an entangled state. It means that the state of the atom, if you make a measurement, you will find the atom in E or in G. And if you find the atom in E, you will be sure that the photon number is 0. If you find the atom in G, the number of photon is 1. And this will happen even if the atom has left the cavity. And in principle, the separation can be as large as we want, and it's typically the entangled state situation that was what is interesting in quantum information science. You can also, after you have entangled the atom with a field, stand behind another atom and then entangle the atoms together. And you can, in this way, do some kind of knitting of entanglement between a sequence of atoms crossing the cavity. And this is a demonstration of basic quantum information processes. But I will stop here about these experiments because they were done already 10 to 15 years ago. And I would like to go to the second part of the talk where we are exploiting the Redberg atom interaction. So if you consider 2 Rydberg atoms, which are at a distance r from each other, the interaction between them is very simple. It's just the product of the dipoles divided by the cube of the distance. This is called the van der Waals interaction. It has been known even before quantum physics. Van der Waals got a Nobel Prize at the beginning of the 20th century before quantum physics was developed. And this gives rise to 2 kinds of interactions. The first one is a non-resonant interaction, which shows that if you have 2 atoms which are prepared in the same Rydberg state, their interaction will shift their energy by an amount which is proportional to the square of the interaction. Why? Because this level, the 2 atoms excited, is non-resonant with all other levels. If you want to couple it to some other level, you have to excite one and to de-excite the other, and this process does not conserve exactly the energy. So it's a non-resonant process, and quantum physics tells us that a non-resonant process occurs at the second order. And if you want to estimate how big the process is, each dipole is proportional to n squared. So the van der Waals interaction has a power n to the 4th. If you raise it to the second order, you get n to the 8th, and you have to divide by the energy difference of the nearest level, which scales as 1 over n cubed. So n to the 8 divided by 1 over n cubed give you the n to the 11 enhancement. So it's a huge effect. If you go from n equal 1 to n equal 10, you gain 11 orders of magnitude on the size of the effect. And in spite of the 1 over R6 law, you still get an interaction at a very large distance. You have another kind of interaction which is resonant in the case when, by chance, this doubly excited state is exactly resonant with a structure in which one atom gains energy and the other one loses energy. And you can reach such a situation, for instance, by applying an electric field which tunes the initial state to the final state energy exactly. This is called a Forster resonance, and this one is even larger. It's scaled as 1 over r cubed because it acts as first order. I don't have time to discuss that, so I will restrict myself to the van der Waals 1 over r6 interaction. What you have to do is quite clear if you want to study that in a quantitative way. First of all, you have to excite the atoms to a Rydberg state, of course. Then you have to keep them at a fixed distance and orientation from each other, so you have to trap them and to manipulate them spatially so that they don't move. Then you have to detect them selectively to find out whether they are excited or not. And you have also to try to tune their interaction by applying electrical and magnetic fields to the system. So this recipe, I will follow this recipe and try to explain what we do. First of all, how do you excite them? When you have an atom in the ground state, if you want to promote it to a Rigberg state, you have to use laser excitation to a low angular momentum state. And the way it is done now is a coherent process in which you have the atom absorb 2 photons of different colors. And we try to avoid to be resonant with the first process because we want to have a coherent two-photon excitation to preserve the quantum superposition of the atom between the ground and the excited state. So we do that with two colors, and there is a detuning delta for the intermediate state. And we observe the Rabi frequency. If you count after a given time, you find out where the atom is, and you do the experiment many times, you can reconstruct the probability for the atom to go from one level to the other as a function of time, and you get the kind of curves that I show here. It's again a Rabi oscillation, but of a slightly different nature from the previous one. Here, there is no entanglement between the laser and the atom because the laser field is classical. It contains a huge number of photons, so the laser field is just a classical device which allows us to prepare superposition of atomic states. The effective Rabi frequency omega is, of course, the product of the amplitude of the field on the two transitions. So it's a product of the two Rabi frequencies on the first stage and the second stage divided by the energy mismatch delta. And you have to add, if you want to be complete, a light shift because each of these non-resonant lasers slightly shifts the energy level of the atom. So if you detune the two photon transition from the atomic transition, you have to take into account not only the detuning of the laser, but also the detuning produced by this light shift effect. How do you detect the Rydberg atoms? In fact, you don't detect them. What you detect are the atom left in the ground state. What you do is that you apply, after you finish your experiment, you apply a laser which is resonant with the transition from the ground state to the first excited state, and you look at the fluorescence of the atom. So the atom goes through a lot of cycles, and a lot of photons are detected by a microscope into a detecting device. So you get a very high efficiency, but you see the atoms only in the ground state. If the atoms are in the excited state, you don't see them. So that's a basic point about the way the detection is made. Now, the second point is how do you keep the atom quiet, motionless? For that, you use what is called an optical tweezer. An optical tweezer is just a laser beam which is focused very strongly, and the light intensity is very strong at the focus, and it is a non-resonant light, but this light produces a force on the atom which brings the atom at the maximum of the field intensity. So this tweezer have been discovered, this tweezer effect has been discovered almost 50 years ago, and Arthur Ashkin got a Nobel Prize for that 2 or 3 years ago, 50 years after he made this discovery. So you see how the setup works. You have a laser, which is, the laser beam is focused here in the central part of the setup. You have a gas of cold atoms, and if an atom is just at the focus, it will be trapped in this potential well, which has a dimension of about 1 micrometer. And another laser is used to induce fluorescence. So beam splitters separate the fluorescent light detected here, and you see the atom. And you see this atom by an increase, when an atom falls into the trap, the fluorescence increases. When the atom leaves the trap because of a collision with another atom, suddenly the fluorescence disappears. And the level of fluorescence tells us whether there is 0 or 1 atom in the trap. It turns out that you cannot have more than 1 atom in the trap with this detection procedure, because if you have 2 atoms, the laser light will excite this quasi-molecule, give a lot of energy to it, and this energy will be enough to expel the 2 atoms from the trap. So the only thing you can have left in the trap is either 0, no atom, or 1 atom. The last one, if you have an odd number of atoms, all the atoms are expelled except the last one. So this is a good way to excite a single atom, but it's a non-deterministic way, because when you do the experiment, 50% of the cases you get 1 atom, and 50% of the cases no atom, so the excitation is strong. Now, an effect which is very important here, and which is really the most important physical effect which makes this physics interesting, is the Rydberg blockade effect. I describe here a very simple experiment in which you prepare 2 tweezers, and you can do that very easily. You just have a lens, you focus the light with a laser, and then you have another laser beam which makes just a very small angle with the first one, and you get 2 spots instead of 1. In this way, you can trap atoms at a well-defined distance from each other, going from 0 to, let's say, 10, 15 micrometer. And when you apply this double tweezer to a gas of cold atoms, 4 things can happen. Either you find that the 2 traps are empty, or the 2 traps counting 2, each one atom, or there is 1 trap empty and the other one with 1 atom. And of course, the case which is of interest to us is when you can trap 1 atom in each trap, because then you could have 2 interacting Rydberg atoms. So once you have 2 atoms in a trap, you use a laser to excite them into Rydberg state. The first excitation is quite clear. You go from the ground state to the Rydberg state if the laser has the right frequency. But once you have done that, you cannot use the same laser beam to excite to the second state if the atoms are too close to each other, because the atoms repel each other or attract each other. The van der Waals force can have either sign depending upon the structure of the levels. Here, I describe the case where the levels are repelled, and you see that the second excitation becomes off-resonant if the atoms are too close. You see that this process introduces a Readberg, a distance RB, which is a distance of blockade. If the atoms are closer than this distance, they cannot be excited by the laser. And this distance depends upon the strength of the laser. If you increase the strength of the laser, of course, the line will be broadened by omega, and then you'll be able to excite them. So this Rydberg blockade effect does forbid to excite a Rydberg atom in the vicinity of an already excited one, depending upon the laser intensity. Another very important feature is that when you excite the first excitation, the laser beam having a large waist compared to the distance between the atoms, the 2 sides are excited symmetrically. And so what you prepare is a superposition of the state in which it is the left atom which is excited and the state in which it is the right atom which is excited. This state is entangled. So you see that the blockade effect automatically entangles the 2 atoms. So it produces entanglement, and you can show in quantum information that as soon as you have a process that produces entanglement, you can transform it very easily into a quantum gate. That is, 1 atom just drives what happens to the other one. 1 atom can be considered as the control qubit and the other one the target qubit. So this leads to a lot of interesting physics in terms of quantum gates. We can also remark that this collective oscillation, which occurs between the 2 atoms in G and 1 atom excited, occurs with a coupling omega square root of 2. The coupling is larger because of the fact that you have 2 possibilities, so it's a factor of 2, and the normalization of the wave function divided by a square root of 2, and you get an omega square root of 2 effect. You can generalize that if you excite now n, if you have a gas of n Rydberg atom inside the blockade radius. Then you can excite only one of them, but you don't know which one. In fact, you prepare a superposition in which the excitation is collectively shared between all the atoms, and the coupling now is omega square root of n. So you get a faster coupling, and all this has been studied. I don't have time to describe the experiment. Very beautiful experiments have shown that it works that way. Now, what you can do is to observe this blockade effect by varying continuously the distance of the atom with respect to the van der Waals interaction. So if the atoms are far away from each other, which you see at the top of this slide, then the laser coupling is larger than the van der Waals interaction, and so the atoms behave independently. And you can measure the probability to have the 2 atoms excited and the probability to have only 1 atom excited. The probability to have 2 atoms excited is very simple. For each atom, it's sine square omega t. That's the Rabi oscillation. If you have 2 atoms, it's sine to the 4th omega t, and you see indeed that the curve that you observe is a sine to the 4th power oscillating between 0 and 1. Now, the probability to have 1 atom out of 2 excited is PRG plus PGR, and each of them is just sine square omega t times cosine square omega t, because you need the probability to have excited one and not the other. And so you have twice sine square omega t cosine square omega t, which is just 1/2 of sine to the square 2 omega t. And you see now that it oscillates twice faster from 0 to 1/2. So what you see at the top is the behavior of independent atoms. At the bottom, you look at what happens, on the other hand, if the atoms are close to each other, so that omega is smaller, much smaller than the van der Waals force. Then the probability to excite the 2 atoms is 0. You don't see the 2 atoms excited. and the probability to excite only one atom is just sine square omega square root of 2t, as I said before, and you see that the experiment confirms that. So you have a well-defined behavior at above and below the blockade regime. You can also study experimentally the intermediate cases, and you see how this oscillation becomes complicated between the two limiting cases. From this oscillation by Fourier transform, you can get the eigenvalues of the Hamiltonian, which couples the three levels to each other. And from that, I don't give the details, you can measure experimentally the van der Waals interaction. And you see how the van der Waals interaction here for three values of the principal quantum number, the values 53, 62, and 82, vary with the distance. It's a log-log plot, so you see this very high slope, very big, large slope, which shows the 1/R6 variation. And for a given distance, for example, here you see that when n is going from 53 to 62, which is a change of 20% in n, you get 2 orders of magnitude difference in the value of the effect. So you see the huge n to the 11 power law on this kind of graph. So this kind of experiments have been done in different groups. I will give the reference at the end, which proves that you can really control the behavior of two atoms. Now the next step, of course, is to do that on a sample containing a large number of atoms. So you have to put atoms at a well-defined spot in a lattice. There are two ways to build the lattice. One way was done about 10 years ago by the group of Emanuel Bloch in Munich. He used interfering laser beam to build an interference structure in 2 dimensions, which is just an ordered array of potential wells, that is potential optical tweezers. And he puts that inside a cold atom ensemble, and so the atoms are trapped in the different wells. And he looks at the atom with a high aperture microscope. And you see the kind of spots that he sees in this experiment. So the atoms are ordered in this lattice. Then you use a couple of lasers to excite to Rydberg state. So the principle of the experiment is the same as the one I described for 1 or 2 atoms before. You see here the kind of ordered structures that you can see in the ground state. To see the atom in the ground state, you just illuminate them with a fluorescence laser beam, and you see you can really resolve the position of the atoms in the structure. It looks like a ring here with a vacuum in the middle. In fact, what happens is that the atoms like to be away from each other because they repel each other. So you get one atom in each well. And if there are an excess of atoms, you will get 2 atoms, but in the center, because the potential is deeper in the center. It's a kind of parabolic potential. So it looks like a wedding cake with different levels. But of course, in the center, you have 2 atoms, and the 2 atoms expel each other from, so it appears as 0, but in fact, before you applied the fluorescence light, it was 2 atoms. So you get this kind of ring structure if you have too many atoms. And this is called technically a Mott insulator. It's a model something which was predicted in condensed matter physics and observed clearly for the first time with these cold atoms. Then you excite the atoms into Readback states, and what happens is that the atoms can be excited if they are far away from each other. How do you detect these atoms? It's very simple and very clever. What you do, once the atoms are excited, you send a laser which just push away all the atoms which stay in the ground state. So you empty completely the ground state, and then you send a laser which, by stimulated emission, brings the atoms which are in the excited state down in the ground state, and then you apply fluorescence. So you see only the atoms which have escaped the washing out process in which you expelled all the atoms in the ground state. And what you see is shown here. If the laser excitation is weak, you can see 2 atoms. If you have a stronger laser excitation, you can see 3 atoms, 4 atoms, or 5 atoms. So what happens is that depending upon the strength of the laser, that is on the Rydberg blockade, the system can accommodate 2 atoms if they are far enough from each other. This is the top slide. If you increase the coupling, 3 atoms will be packed into the system, but they will like to be at the summit of an equilateral triangle to avoid each other. 4 atoms, it's at the tops of a square, 5 atoms is a pentagon. And if you do the experiment again, you will find the same picture, but with a different angle, because it's random. The measurement randomized give you one of the possibilities. In fact, what you prepare is a kind of quantum crystal, which is a superposition of all the possibilities of the two atoms in different directions, and you see only one of the outcomes. To see that, Bloch and his colleagues have just summed up a large number of realizations using the same axis of symmetry for the problem, and you see that indeed you have 2, 3, 4, 5 spots which make up a line, a triangle, a square, or a pentagon. And this is the experiment, and you see here the theoretical simulation. So these are beautiful experiments, but in this experiment you don't control each Rydberg atom independently from the others. I will finish by describing what has been done during the last years, which is very, very clever, which is to build a lattice by arranging a structure of tweezers which are produced by holography. What we do is shown on this slide. You have a device which is called a spatial light modulator, which is made of separated pixels. Each pixel is a small LCD, a small liquid crystal device, in which you can control the index of a fraction of the liquid crystal by an electronic procedure. And so each pixel can induce a different phase to the light beam. So you can tailor a phase distribution on your light beam, which is reflected by this spatial light modulator. And to make a long story short, when you focus this light beam, at the focus you get the Fourier transform of this spatial distribution, which you can adjust to get any kind of field distribution that you want. So it's no longer an interference of laser beam, it's an interference produced by the Fourier transformation of the focusing lens. And you see here how the experiment works. Now you have your laser, you reflect the laser on this spatial light modulator, you focus it here, and you get here the Fourier transform, and then you use the fluorescence laser light to detect with this camera, and you see, what you see is shown here. When you fill up your tweezer array, one side out of 2 is filled because of the fact that you have either an even or an odd number of atoms which are trapped, and you see only 1 or 0. Now, if you want to have a regular lattice, what you can do is to take atoms at the periphery with another tweezer and move it to fill the holes that you have in your lattice. And in a very short time, you can get an assembled configuration in which you have filled everything. This is very beautiful because it's a kind of Maxwell demon in action. You see, you get information, a computer uses information to decrease the entropy of the system by filling the parts which are empty. I think I have to go faster, but almost finished now. I just want to mention that there is a French startup company called Pascal, which is making these arrays of atoms, and I think you can buy it. It costs a lot of money, but if you want to speed up your research, instead of doing that, which will take you 2 or 3 years at least to achieve, you can just buy this. And this is, I do this kind of advertisement for free. I don't get any money from Pascal, but I think it's the use of this startup is just to provide devices which can be used for science by researchers doing basic science. So with this system, you can simulate what is called the Icing model of condensed matter physics. You have atoms at each side, and these atoms have 2 relevant energy levels, the ground state and the Readback state. The ground state can be considered a spin down, the excited state is spin up. And you can couple these 2 spin states. They are coupled by the van der Waals interaction, and they are coupled by laser excitation at frequency omega, and you can also play with the detuning of the laser excitation from the transition. And you have all the sites occupied, and you know exactly what is the distance between 2 atoms, so you have all the elements to control the Hamiltonian of this 2-level system. The laser field that you apply, which induce the Rabi frequency, can be considered as, in this model, as a transverse field, because it makes the Lamour precession of the spin from the up and down level, which is a Rabi oscillation. On the other hand, the detuning, which shifts the energy levels, is equivalent to the longitudinal component of a magnetic field. So what is the Hamiltonian of the system? The levels are coupled to each other by the van der Waals interaction between the Rydberg atom, which realizes the Icing coupling. And this interaction is strongest for nearest neighbors because it decreases very fast with distance. The Rabi oscillation induced by the laser emulates the coupling to a transverse field, a field which is perpendicular to the quantization axis, which defines the spin up and down states. And the detuning is equivalent to the coupling to a longitudinal field, be parallel to the quantization axis. The van der Waals interaction is C6 over R to the 6, and the Ni occupation number is just the projector on the upper spin state. It's a very simple operator, which is proportional to 1 plus sigma z. So you can express all this in terms of the Pauli matrices. And all the parameters are under control. So I would just very briefly describe a beautiful experiment which was performed by Antoine Brouwais at the Institut d'Optique in Paris. They filled a square array of 14 by 14 atoms, regular array, a square lattice, and then they applied adiabatically, very slowly, they varied the amplitude and the detuning of a laser field in order to get to the antiferromagnetic phase. And you see how it is shown here. 1 out of 2 sites is occupied. In fact, the other side, you don't see it, but it means that the atom is in the up Readback state. So you see that in this antiferromagnetic structure, each spin up is surrounded by a square of spin down. So this is the antiferromagnetic structure. You can do it other ways by having a triangular array, not a square array, triangular array. And in this case, what you see is that the structure is different. Each spin up is surrounded by an hexagon, 6 atoms in spin down. So it's an antiferromagnetic phase which is different from the previous one. And how do you get this? Very simply, you start by all the atoms are at the beginning in the ground state here. You start with a large detuning. You increase the laser field first, so it's very far from resonance. On this axis, you have the offset of resonance. On this axis, you have the Rabi frequency. So you are far from resonance, and when you get to this amplitude, you slowly decrease the detuning to enter here to the positive delta value, small one, and then you decrease the light intensity, and you come down again. The atoms are again in the dark, and then you are in this phase, and the theory shows that the transition between the 2 phases is given by this curve. So when you enter in the blue zone, you go from the paramagnetic to the antiferromagnetic phase, and experimentally it works. It's a kind of analog quantum computing because you don't use quantum gates, but you use the fact that you are able to control the Hamiltonian of the system to bring it to this phase. So I want to make one remark. First, you have to go slowly enough so that you have many Rabi oscillations occurring during the process. And you have also to go fast enough because there is a big drawback in this problem is that when the atom is in a Rydberg state, it is no longer trapped. So after a very short time, the excited atoms are expelled. So you have to do everything fast compared to the time it takes for a Rydberg atom going to a few meters per second to escape for a few micrometer big trap, which takes a few microseconds only. So you have only a few microseconds to do the experiment. But still, you see the experiment works, and it's one of the first experiments in which this kind of thing has been done. There is the group of Antoine Brouwais in Paris and the group of Misha Lukin in Harvard, MIT, and they are doing similar experiments. But what is the next stage? The next stage is, of course, to trap also the Rydberg atoms, because if the Rydberg atoms are also obliged to stay here, you have a much longer time to do the experiment, and you can really go in the adiabatic regime in which you could observe the quantum evolution of the system over very long times, and then you might see new effects and new quantum phases. So why is it difficult to trap the Rydberg atoms? In a Rydberg atom, you see that the outer electron is almost free. And if you apply, when you apply the tweezer beam, what the tweezer is doing is just shaking the electron in its orbit. This shaking gives it a kinetic energy of vibration, and this is a positive energy. And this is the energy of vibration you get is given, it's a simple exercise of undergraduate, even high school. You get this energy, which is positive, which means that in fact you have a potential hill here and not a potential well. So when the atom is in the Rydberg state, it rolls out very quickly from the trap and escapes. So, and this explains why you have only a few microseconds to do your experiment. So if you want to trap the Redberg atom, you have to make a hollow trap. You have to make a trap in which you will have walls all around, light walls all around the Redberg atom. And this can be done. It's just a matter of changing the phase distribution of the laser beams, and you build what is called a bottle beam trap or a bob trap to say it faster. And you see now that your experiment becomes more complex but still doable. What you have to do is to have two different space light modulators, one which with a laser beam which prepares a tweezer trap, and another one here which prepares the bottle beam trap. And you have to alternate between the two traps. So I summarize here, you have a first system which prepares the tweezer for ground state, and you have another system of holographic SLM which prepares the trap for Rydberg atoms. And then, of course, when you focalize the light, you have either one trap or the other, two different phase masks for the two traps, and the atoms are trapped against the focal plane of a short focal length. I give you here the experimental sequence of an experiment that we did in my group. Michel Brune and colleagues have done this experiment in Paris at Collège de France and Laboratoire Castor-Bruxelles. You see that the process is rather subtle and a long one. You start by preparing a tweezer trap for ground state atom, and you filled it with an array. You rearrange the atom. Here we have done it with 18 atoms, 6x3 trap, so it's a very small first step. Then you switch up the tweezer, and very quickly you excite low L, low angular momentum Redberg atoms with lasers. And before they have time to escape, you switch on the bottle beam trap, and you excite this atom into a circular state. So this is you add radio frequency microwave to prepare the circular state. So, and I remind you the process, you apply an electric field which leaves the degeneracy of this state, and by a adiabatic process, you increase the angular momentum, and you get into the circular state, and the circular state are held on in the bottle beam trap. Then you wait for a given time just to show that you can keep the atoms, and in the end you do the opposite. You bring the circular atoms down to a low angular momentum state, you switch off the bottle beam, and very quickly you de-excite the atom by stimulated emission down to the ground state. And once they're in the ground state, you switch on very quickly the tweezers, and you switch on the fluorescence, and you look at what is left. So it's a long sequence, but it works. And you see the result here. If you put no trap, you see that very quickly the number of atoms decreases. So you lose the atoms after 25 microseconds. And if you apply the trap, you see that the atoms survive. This is the first result. You see that the atoms survive much longer. How can you find out that you have indeed all the features that you want? They did a very simple trick. They displaced the tweezers from the bottle beam by a small amount, which means that when you switch on the bottle beam, the Rigberg atoms are not at the bottom of the trap, so they are oscillating with a fast velocity. And they start oscillating, and in the end, when you switch again from the bottle beam to the tweezer trap, you recapture the atoms if they are only the right phase in this oscillation motion. And you see indeed that the number of atoms that you recapture is oscillating depending upon the delay between the first and the second switching. And this frequency occurs at 17 kilohertz, which is exactly what is expected from calculation. So indeed, we are able not only to trap the atoms, but also to prepare a coherent oscillation of these atoms. So this is only the beginning, and I just on this last slide give you what we will try next, what they will try next. The setup is ready to study interaction between circular atoms, so we can load circular atoms, trap them. At 15 micrometer distance, the coupling is of the order of a few megahertz, so it's a large coupling, and you can study that. But we have another limitation, which is we were working at room temperature. At room temperature, you have a lot of blackbody radiation, which induce transition and which limits the lifetime of the circular state. To increase the lifetime, you have to go to a cryogenic system like we did in the cavity QED experiments. And so we are there in the process of transferring the existing setup to a 4K cryogenic environment, which would increase the lifetime to about 10 milliseconds, leaving a lot of time to do experiment. 3 orders of magnitude longer than what we had in the previous experiments. And we can go even further if you do the experiment between two metallic plates which are close enough for each other. We can completely inhibit spontaneous emission of circular state. In fact, this was a very beautiful experiment performed for the first time by Dan Kleppner already 40 years ago. He showed that between plates, a circular state survives almost indefinitely because there is no mode into which a circular photon can be emitted. So I think this computer works by itself. He wants me to finish, so I will just conclude by saying, by just emphasizing the fascinating evolution of AMO physics during my career. When I started about 50 years ago, atomic physics was dealing with large samples. You see here, it's a picture of Alfred Kastler, which is holding its optical pumping cell. In this cell, you have 10 to the 10 to 10 to the 11 atoms, and the signals that we see, the optical signals, are an average of what you see with a huge number of atoms that you don't control. And you don't see quantum superposition, you don't see quantum jumps. It's a very statistical measurement. Then at the end of the 1970s, we have started to be able to isolate single atom. And this picture is historical. It is the first observation of a single ion in a trap by Peter Toshek in 1978. So you see a very faint spot in the middle, which is the first observation of a single atom fluorescing a lot of photons into a microscope. And from then, we went from a large number to 1, and now we are going back to a large number again, but this time by controlling all and of course, all this is thanks to lasers. Without the lasers, all this would have been impossible. It's thanks to lasers, but also, and above all, thanks to many co-workers and colleagues, and I will finish by acknowledging them. First of all, I want to acknowledge Jean-Michel Raymond and Michel Brune, who have been my students first and then my colleagues and collaborators for all over my career. And I have done with them all the cavity QED and with Redberg atom physics. I want also to acknowledge the idea of the Rydberg blockade, which was given independently in beautiful papers about 25 years ago by the group of Peter Zoller, Misha Lukin, Ignacio Sirac in Germany. The experiment I have shown to you about the Rydberg blockade and the Rydberg paramagnetic to antiferromagnetic phase transition were done by Philippe Granger and Antoine Brouwes and their colleague at the Institut Optique Group in Paris. And similar experiments have been done in Madison by the group of Safman, Walker, and all. And there is also the group of Misha Lukin and Vulicic at MIT and Harvard, but I did not describe the experiments. And the trapping of circular Rydberg atom is done in our group in Paris by a group which are led by young researchers Clément Serrin and Sébastien Glaise and their student at the LKB. And many other groups around the world are competing to try to get the best out of this physics. And thank you very much for your patience.
Okay, thank you very much for that excellent, wonderful talk. So I think we have time for some questions. So please raise your hands and a mic will come to you. I believe this is recorded. Yeah, please, Naveen over there.
Yes, I have a question. Why is the lifetime of Rydberg state so large? Why isn't there spontaneous emission?
Because spontaneous emission rate is proportional to the square of the acceleration of the, classically it's a classical process, proportional to the square of the acceleration of the electron on the orbit. And if you go into Rydberg state, because R is large, the acceleration is much smaller than for ground state. And so they radiate much less.
But isn't it also just proportional to cube of the frequency difference between the excited and the ground state?
Yes, no, but they cannot go to the ground state because of angular momentum.
Angular momentum, okay.
N can go only to n-1, which is a microwave transition, so
it's conservation of angular momentum.
The omega cube is very small because of that, but this is also explained by the classical argument about the acceleration. All is consistent.
So you conserve angular momentum, so you cannot go to ground state?
By 1 photon, no, you cannot.
Thank you.
Because it's a circular state.
Thank you.
Yeah.
Okay, more questions? Yes, please, Vijay, mic to Vijay.
Thank you, Serge, for that wonderful talk. So my question is also related to the lifetime of the states. So earlier you had mentioned that when you go from the elliptical to the circular orbit, the lifetime increases to milliseconds, maybe even a second. But right at the end, you talked about the enhancement of lifetime between two plates.
Yes.
Where the previous numbers were again back in the microseconds. So maybe I missed something in this experiment. Why was the lifetime lower in these experiments involving multiple Redberg atoms?
Okay. In the experiment they described, the temperature was not controlled. It was at room temperature, so you get a huge enhancement of the emission rate due to stimulated emission by blackbody photons. So if you go to, in order to get the long lifetime, you have to be in a cryogenic environment, which we did in our cavity QED experiment before, but which we have not done yet with this tweezer experiment. So if you go to the circular state, the lifetime for n equal 100 is about 1 second.
At room temperature?
No, at very low temperature. And you can increase it to minutes or even hours in principle if you put it between plates, because then there is no place for no mode for the photon to be emitted into. So we hope that we'll be able, maybe not increase to hours, but at least to many seconds, so that, because what matters, if you want to have a purely coherent process, is that not a single atom in the ensemble radiates. So you have to divide a lifetime of 1 minute by the number of atoms. If you have 60 atoms, it means that you get a lifetime for the system of 1 second, which is a huge amount, which is huge compared to the Rabi frequency, which is megahertz. So you can have millions of cycles before the system loses its quantum coherence. And we really hope, Michel Brun and colleagues have written a theory paper in which they show that they can tailor Hamiltonians, which allows them to observe different kind of quantum phases if they are able to observe the system over a long period of time.
Thanks.
Yeah.
So, quick question over here.
Yeah, my question is regarding the first part of your talk. So when you said this inside the cavity, you start with your atom in the Rydberg state,
Yes.
then the one photon is emitted,
Yes.
then there is an oscillation,
Yes.
which you call Rabi oscillation, vacuum Rabi oscillation.
Yes.
So there is actually a real photon in the cavity at that point, which is
Yeah, in this experiment, yes, there is if you just stay for half a Rabi period, you prepare exactly 1 photon.
Okay.
Yeah.
So is there a chance that actually if you start with the system, the atom in the ground state and also with no photons, then due to vacuum fluctuations, you get the atom excited to the Rydberg state? violating the conservation of energy?
No, first of all, it's not the ground state. The process occurs between two Rydberg states with n differing by 1 unit, let's say 51 to 50. And when the upper state enters, it is in vacuum, so you can say that, in fact, the emission is stimulated by the vacuum fluctuation. The system goes from 0 to 1 photon. And then since this photon can stay in the cavity for a long time, it can be reabsorbed and the atom goes to the upper state. In fact, it's a two-level system which oscillate between E0 and G1. And this is the basic phenomenon. Now we can study other things. We can go out of resonance. If you have one photon and the system is non-resonant, then the atom will be shifted by a small amount without being able to absorb the photon. And if you can measure this shift, the atom is a non-destructive probe of the photon. We have been able to send thousands of atoms one after the other, and they all agree with the fact that there is one photon in the cavity. So it was the first time one could measure a field without destroying the photons. And this process is used now routinely in circuit QED, in which the experiments are done with artificial atoms and waveguides or superconducting cavities coupled to the junctions. And this non-destructive measurement of photon is used to prepare Schrödinger cat states of the field and to make quantum error corrections based on the fact that you can detect the emission or absorption of a photon without perturbing the system. So it's this Schrödinger cat system and this non-destructive measurement of photons are being used in practice with devices which the authors say might lead to a good way of controlling errors in this system. So it's still in the domain of basic science, but you see how these processes can be used for practical applications.
Okay, a quick question by Himadri and the last question by the gentleman there after that. Himadri, please.
Yeah, hi. Thank you so much for the very nice talk. So I had two questions actually. The first one is, like when you have a single Redberg atom, the main criteria was trying to get as strong coupling as possible. But again, then when we go to the array, we really don't have a cavity. So how is that strong coupling between light and matter achieved? Or
The coupling is due to the fact that the electric dipole of the atom is very large. So it's.
But we don't have any cavity in the second case, right? Like with the many Redberg atoms.
No. In this case, it's not the cavity. In this case, the coupling is large because the van der Waals coupling is a product of the dipole of the atom. So you get a very large coupling if the two atoms are in a Readback state because of it.
So the light-matter interaction is completely semi-classical.
Yeah, in fact, you can say that each atom is highly polarizable in the field of the other. So you have a huge polarizability because the dipole is so big. And this explains the enhancement. The fact that the atom they interact up to 15 micrometers from each other, which is a huge distance at the atomic scale.
Yeah, and the second question I have is, like when you have an ensemble of emitters,
Yeah.
one issue you have is inhomogeneity that creeps in because of the transition frequencies are not often the same. So is that an issue while working with Redberg atoms?
No, because these atoms are all identical so they radiate at the same frequency. This is a big advantage compared to to artificial atoms which are man-made and which don't have the same frequency. Here, the sample is very small compared to the waste of the laser beams which are used to detect or to trap. And so you can control this inhomogeneity to a good extent. But I agree that if you want to reach, if you want to do real quantum computing and make sure that you have a fidelity of it to the gate very high, then these issues will become important.
Thank you.
Okay, so last question by this gentleman over there.
Thank you, sir. So my question is, like, mostly here we are dealing with Rydberg atoms, and in that case, the principal quantum numbers are very high, for around hundreds. So, but my question is, how we can deal with for a molecule, like how we can find the Rydberg states for a molecules? There are so many other interactions that can form within a molecule. So, what one should do to deal to find the Rydberg states in a molecule?
I think you have Rydberg state molecule, but the structure is more complicated because you have to take into account the coupling of the electronic motion with the vibration and rotation of the molecule. I know that there have been studies in that. Even cooling molecules is more difficult than cooling atoms because the transitions are open. You know, what you say reminds me of a saying of when I did my postdoctoral work with Arthur Chalot in Stanford. He used to say, even a diatomic molecule is a molecule with one atom too many for this simple physics.
Okay, on that wonderful note, let's thank Professor Haroche for this wonderful talk again. And
thank you.
And as a token of our appreciation, I invite Professor Milind Atre to present him a small token.
Yes. Yes.
Thank you very much for the wonderful talk.
Thank you. Thank you for your welcome.
Small token from IIT Bombay.
Thank you very much.
Maybe.
I will not open here, but thank you. Thank you.
Excellent. And there's some high tea served outside, which we invite you to. Thank you very much. So we meet again tomorrow morning, and we'll see you there.